Cool. Amazing. Let's start, and whoever comes. So, what we're gonna discuss today is about machine learning modeling in a parallel world, as I call it. But it's about how you can distribute machine learning problems and how you can think of a machine learning problem as a life cycle or as a pipeline, as you wish, of different steps. And then we're going to focus on each step and see, okay, what we could do to distribute or optimize this part of the pipeline. And before we start, a little bit about me. I'm Maria Zervou, I'm Greek, and I've been working as a senior specialty solutions architect on Databricks. So my specialty is more machine learning, MLOps, and data science work, which means that I'm working with different customers across different sectors, mainly focusing on media, entertainment, and telco, and some retail lately. So, I'm working with different customers on solving or optimizing these kind of problems. So more MLOps platforms, and machine learning and data science optimizations. So on Databricks, which means that behind the scenes, all the technology is Apache Spark based, right? And this is kind of what we're gonna discuss today. But during the talk, you're gonna see some symbols. So one is the attention symbol. So if you see that, pay attention, because we're gonna probably show some things that can go usually wrong. So some bottlenecks in the pipelines. And this is the symbol of impact, meaning when you see this symbol, pay attention, because I'm gonna share some quick wins or quick solutions or quick ways of solving or thinking about the problem. So attention and impact. And the agenda is the following. So we're going to discuss what is the problem, right? Why are we even talking about it? We're going to go through an Apache Spark refresher, how Apache Spark works, what is it, and how it scales. And then we're going to go through the model lifecycle, and we'll go through each step and what can be optimized, and then some key takeaways. Yeah, questions, you can put it in the QA section. We can take it at the end. Or if it's something very burning, feel free to unmute, and ask it. So up to you. So let's start with the motivation. So if you're working with data scientists and people from ML background, usually, we have our laptops, we download the data in our laptop, and we work usually with small data sets, and we work locally, right? So we have some data, we download locally, we solve some models, then we send a pickled model or a ready model to the data engineer or the ML engineer to take that to production. But obviously that is not scalable, right? Because now we're talking about big data and actually a lot of rules and regulations about not being able to even download data on your laptop, right? So now we're talking about big data, which means that big data we cannot do models on our laptop. So this means that we have a challenge, and we're going to solve this challenge. In this case, there are multiple ways to solve this challenge, right? But in this case, we're going to describe on how you can solve this challenge with Apache Spark and distributing the workload across different machines. So why Apache Spark? So first of all, because it has a very large community and it's open source, right? So it's an open source project. You can install it on your laptop or in any VM. So you can just go and use it, right? You don't need to pay anything. So it has more than 1,000 contributors. It's being used across many organizations and has 20 million downloads per month, which means that it's hugely used and maintained by the community as well, right? So it's not only about Spark community, it's about, in general, developing data science, like data engineer community. So it's a very popular project, to be honest. So good to learn and good to know about. In terms of what it is, it's a computing engine, right? So it has, it gives us some optimizations, and we can access those optimizations using different languages. We have R, SQL, Python, Scala, Java, and we can use Spark to solve different kind of problems as well. So we can hit it with SQL queries, we can do streaming jobs, we can do ML, we can do graph ML as well, like graph computations. So it can solve a variety of problems. So not only can help us optimize our workloads or distribute our workloads, it can also help us solve with one kind of system many different problems, which is very nice. And in terms of what it is and how it works, when we're talking about Apache Spark, we usually have this architecture. We're going to say that there's a cluster somewhere to be used, right? And this cluster for us is the compute. So in the cluster, we have some main components, which is the master node, the worker nodes, and the cluster manager. And in the master node, we call it master or driver, usually driver node, right? And in this node, we run our main function, and we have the Spark context there, sitting, waiting for updates. And also, the main role or tasks it has is to convert the user programs into different tasks. So it takes a huge, let's say, program, it splits it into tasks that can be executed in parallel, and then plans how these tasks need to be executed. So this is the driver. Then we have our workers, right? So the driver is just there to kind of build the tasks and the workload that needs to be executed, but nothing is executed on the driver if the program is correctly built. All the work is being done on the worker nodes. So we call them worker or node or worker node. And these are the VMs that execute all the assigned tasks, and they submit the results back to the driver. And here we store some intermediate results as well in the memory or on disks, on hard disks. So we have the driver, the worker, and in the middle we have the cluster manager, whose task or his role is to just keep track of what resources, so which workers are free and we can use them with more work, and then negotiate for executors with the Spark context. So all of these, it's called the cluster, and all of this works very well all together to kind of take all the workload on the driver, then distribute all of these different tasks across different workers. And this is where the scaling can happen, right? As you can see, in a before Spark world, we were focusing mainly on here. We had a VM where we're doing all our work. Now you can see how the parallelization can happen, and this can scale up to as many VMs as you are willing to pay, mainly, right? And it's in VM, you have different cores. So the parallelization is worker and cores as well, right? So tasks are being executed in cores, so there can be multiple tasks running in one worker. So this is what Apache Spark is. And when it comes to ML, the machine learning lifecycle looks like the following. So usually, a data scientist or ML engineer will do something like the following, which is they'll have to do some data preparation, bring the data into a form that can be understood by a machine learning algorithm. And then we have to do the model training, the tuning, and then we have to understand how we can scale the predictions. So after we have a model trained, so how you can use this model to actually predict something. So if we are building a classification model, like a model that would predict if someone will buy my product or not, then after the model is trained, I actually need to use this model in production to actually predict per customer if someone is going to buy the product or not. So let's start with the data preparation. So as we said, usually data scientists were working on their laptops, and now that they have to work and analyze big data, they are stuck with a very common library in the Python world, which is Pandas. Pandas is the main library any data scientist would use to do kind of data frame manipulation, grouping, aggregations, add, remove, create new columns, and etc. right, on a data frame. But Pandas is a library that it's not distributed. So it's not built that way, right? It can't be distributed. So if we take this code, this pure Python code, and we move it into a Spark world, there is no benefit. All the code will run on the driver node, as we saw, and nothing will be executed on the workers because it just cannot understand it. So it can slow down all the data preparation, and obviously, if we load all of this data, we're definitely going to have out-of-memory errors at some point, right? So limited memory. So how do we solve this problem? How could we combine Spark and Python and this Pandas library to actually solve this problem? Well, there is a Spark or PySpark API called Pandas, PySpark Pandas, and it's a wrapper or it's a re-implementation of the Pandas library on PySpark. So it looks and feels exactly the same as a pandas library, but behind the scenes, it actually translates it into a Spark what Spark understands, right? So, and that's amazing. Like that is huge impact because you can just transfer the workload from Python to a Spark environment by using this library now. So instead of importing pandas, you import Spark pandas, and you create your data frame. And after that, you can do data frame operations, but now behind the scenes, these are distributed. So these can actually work on a huge, large scale of data. And that is very big impact. So customers across the world that are using this API now like aggressively because they can just bring the workloads on a Spark environment very easily. Another thing you can do with that is after the point you create a PySpark pandas data frame, because it's Spark behind the scenes, and we saw that we can speak to Spark in many different languages, one of which was SQL, you can actually hit SQL queries on the PySpark data frame, which is Python language. So we're combining Python and SQL together now, which is also very important given that a lot of people out there actually code in SQL mostly, or some join statements or big merge operations are happening in SQL and not that much in Python. So sometimes we are more familiar on creating like these SQL queries instead of writing in Python. So that unlocks a lot of potential as well. Another thing, which is very interesting to think about, sometimes we forget, is about how, so if we want to analyze some big data sets, what we usually do is we read all the data sets in memory, all the data from this location in memory, and then we filter out the required data. So we did a read of all the data in memory. We said, oh, we don't like this data set, let's drop it, or this part of the data set, or I only care about a group of these, or I only care about the location or a group of people out of all of these huge data set, which I've already loaded in memory. And now I'm going to drop it, but I've just loaded all in, right? So what we did here is we had unnecessary reads and writes, right? Unnecessary IO operations, which will fill our memory, right? And we can create out of memory errors unnecessarily. And we also like add latency to our pipeline without reason. So another thing we should think about is how we can load only in memory the required part of the data set that we only care about. So if I care about one geographic location, how can I just load only this specific part of the data set and forgetting all the rest? And I can do that by optimizing how I'm storing the data set and also gathering statistics around the data set. There are many ways to do that. We usually with Spark, we use Delta as a file format. So have Spark as a framework and Delta, which is also open source, as a file format. So Spark and Delta can help us do that, can help us bring in memory and do kind of file optimizations on reads and writes. Very important on the data preparation for the data science world. So this is the only time I'm going to ask you to grab your phones because we have this article which is all about pruning and skipping of files. It's more targeted for data science workloads, so from this kind of persona, but still it's how you can, optimize your data before you go read or model on them. So how you make sure you bring in memory only the required data set before any training or any data manipulation. So that you, from scratch, like from the beginning, from zero, from day one, from day zero of your pipeline, you actually limit the data set and make your pipeline as lightweight as possible from a data perspective. Let me know if you have any questions, right? So we did the data preparation. Now the next thing is the model training. So there's a thought process here because there are different approaches and different things you have to think about when it comes to machine learning and distribution. So question we usually ask is, can my data fit into one machine? And if I have only my driver, could my data fit into that? If the answer is no, so I'm talking about huge data sets, like terabytes of data sets, in that way, there is usually one way to go about, and this is the machine learning library of Apache Spark. So this library, what they have done is they have kind of re-implemented the main data science algorithms in a distributed framework. So if I want to do a classification algorithm, this classification algorithm is just rewritten into a way that can be understood by a distributed framework. So this means that when I'm launching this experiment, right, experiment one, and I have all of this huge data set, terabytes of data sets, I'm loading all this in memory, but because I'm using Spark to read, so I'm doing spark.read this data set, this means that these data are actually chunked up into small pieces and they are thrown into different workers. That's why I can actually load all of it. And then I'm applying this MLlib algorithm now on all of these chunks of data. But this algorithm now is designed to understand that I have different chunks of data, but I'm modeling across all of them. And at the end of the day, which is something we need to notice here, is that some algorithms can be implemented that way or they cannot, right? So there are some like clustering algorithms like k-means that they just from like what the algorithm does, it does not allow you to re-implement it into a distributed framework. And what we do is after you train on all the data sets, you have one model trial at the end of the day and one model trained. So I'm loading all the data set, I'm chunking it up into small pieces, I'm running an algorithm across all of them, and at the end of the day, I have one model out of this process. So it's just one model. So I'm utilizing all the resources of the cluster for this model only because it's very heavy because of the size of the data set. So this means that this is kind of, at this point in time, I can only mainly train one model because these models are very expensive in terms of resources. And the tuning process, when we're talking about optimizing the models in terms of parameters, it kind of have to be in a serial way. So I'm optimizing parameter, then I'm changing and optimizing other parameter, then I'm optimizing something else. So when working with distributed algorithms, usually all the cluster is utilized to train one model with one set of parameters, and then the tuning needs to happen serially. Now, what happens if we can actually fit the data into a machine learning, into a VM, right? So in this way, we have to think of the distributing power in a different way. Since our data are not that big, so they can fit in a big machine, what we can do is we can think of, is our problem, or could we use this problem to actually train parallel models? So this means an example could be as in if I'm working for a retail customer and we have different stores across the country and we want to build a model to predict the sales per store. So what I would do before Spark World is to kind of take the data set, split the data set by store and train one different model per store. What I can do now is that I can group by this store ID and scale it across different workers. So the technology we use to do that, it's called Pandas UTF, grouped map. And what it does is that we get all the relevant data as a Spark data frame, and then we launch different experiments per group key. So this is experiment 1, 2, 3, 4, but actually the data is sent to the one worker. The data for store 2 is sent to other worker, and etc. Right? The data for store 4 is sent to one worker, separate. So the data are separated across different machines. So I'm launching 4 different experiments, let's say in this case, data key A, B, C, D, store 1, 2, 3, 4. And then I'm training an algorithm on this subset of the data now in parallel. So while before I would do this first thing alone, then I would train a model, then go and train another thing, then go and train another thing. Now I'm doing that in parallel, which is absolutely amazing and powerful, right? So in parallel now I can launch as many training runs I want. And at the end of the day, I get 4 different models, different between them because they are trained on a different data set as well. So Pandas UDFs allows us to group by and apply. It's a kind of a Python idea of working. So you group by the key and you apply a function on each subset of the data set. The code looks like that. You have to decorate it. You say it's a pandas UDF and it's a group map, as in I'm grouping for a key, and then I'm applying something on this group. And then we have the Python function who actually does all the modeling, right? So in here, you can see that we actually train just a classifier, an XGBoost model, and we have a training our test. We're evaluating our model, and then we just write it out, right, as a model. So which takes a data frame and returns a pandas data frame as well. So how this works is, if you think our data set are not really nicely put together as in per group key, so our data set can be messed up. And imagine as each color being a different group key in this case, right? So I'm grouping by the colors in this case. So I'm grouping by the key. By grouping, what's happening in a Spark world is that there is some shuffling of the data set across the VMs, and I'm bringing the right data set to the right VM so that I have the same kind of data in the same VM. So store 1 will be in one VM, store 2 in a different VM, store 3 in a different VM, right? And then I'm applying this function we saw on each smaller data set now. And this can happen in parallel. So this means here that because the data are messed up here, and I need to bring them into the right worker, there is some network expenses we're going to say there, because the data need to shuffle and be in the right worker, but it's minimal compared to the result we get at the end of the day. And one thing we need to think about is, because we have different groups of data, right? We may have out of memory errors because of the skewness of the data, as in we may have much more data in one group than another one. And if we haven't planned it, or we are not aware of our data set very well, we may not expect that, and it's going to break the process, right? Because one VM may be too small for the data set or the operation we are applying to it. So think of skews like, before anything, understand your data and what you're planning to do with it. So I'm bringing the data into the right VM, and then I'm using the apply pandas command to just build one model per store at this case. And then out of all this process, instead of doing that serially, one by one, I can just scale it to as many models as you want. We had a customer who actually was creating 300 models in parallel, and that is absolutely fascinating, because before they had to do one by one. So this is very strong, very powerful, very easy to implement as well. And there are many different use cases as well in different industries, like IoT devices, train one model per device. In the real estate, train different models per geographic location, different models per stock. In retail, sales forecasting per physical stock optimization in supply chain, a lot of use cases. And propensity models per product for marketing in any industry, right? So these are use cases that can be very well solved with that. The other thing we can do is, when we are here, we can think that our data can fit into our machine, and we don't care about doing this parallel model training. The other thing we can scale is, of course, the tuning of parameters. So in every modeling process, we usually do a lot of trials to optimize the model based on different parameters that can fit into the algorithm. So this is an expensive process and needs to go through many iterations. And usually this happens also serially. We call it grid search, where we define a space of different values to try. And then we go and try each different combination, and we track all the different results. And then based on the best result, we choose what is the optimized model. But this is painful. This is very slow, and we needed a solution out of this, right? And in a distributed world, what you can do is, in this case, because we're tuning parameters, well, before we split the data set and we send different chunks of data in each worker, in this case, we are copying the data, all the data, we are copying it into one VM. And then we spin up different model trials, exactly the same. The only thing that changes is that the parameters are different. So while the data are the same here, the parameters are different between each of all of these, as in if we take the depth of the tree as a parameter, like how deep we go into a tree model, it can go from 1 to whatever, right? So this can be 1, this can be 10, this can be 50, this can be 100. So while I have the same data set, I'm tweaking a little bit my parameters on the algorithm, and at the end of the day, I'm getting different models because of the different in the hyperparameters. So in this case, I'm going to have 4 different models, out of which I want just the best based on my KPIs, which can be accuracy, precision, whatever I'm modeling for. So I'm choosing the best model out of all of these models. So I'm doing all of this process just for optimization of my problem, and I choose just one model out of all of these. But in a before kind of distributed world, I had to do that one by one by one by one. And I can have multiple combinations of parameters that I need to try, which was very painful. So this is also very cool. In order to solve that, we use a specific library, which is called HyperOpt. And it's open source as well. It's very flexible. We have different ways of solving these problems. One I said was grid search, which is just you give all the range of parameters you want to try and just goes and tries every possible combination. But obviously that is too slow and expensive. So then there is the Bayesian optimizer, which is focusing on trying to learn from the results and optimize the space on which I'm searching so that I don't search combinations that phenomenal, like possibly they won't give me good results. So it's not random and it's not a grid search. And we use the Spark trials for us to use it with Spark and integrates with other MLflow, like open source libraries like MLflow for tracking of models, very useful as well. And one question we may usually have here is, if you know what is Bayesian optimization means that it's not random, as we said, and it needs to get some information in order to optimize the next run. But if we do things in parallel, how can we pass this information when we do things in parallel for it to learn? So how this happens is, as we said, we spin up 4 different experiments or 4 different runs. We copy all the data inside. These are exactly the same data. And then we spin up different model trials with different parameters, as we said. This has different parameters to this, to this, to this. And I'm waiting. And some of these may finish earlier than the rest. So from the moment one finishes, model trial finishes first, what I'm doing is I'm taking the results, I'm optimizing my hyperparameter space, and I'm kicking the new trial based on the information I got from here. In the next trial, I have a new thing. I got more results. I'm optimizing my space, limiting my space and where I'm looking for the best hyperparameters. And I'm kicking off a trial 6 and trial 7 also. And then when trial 4 finishes, I'm kicking off model trial 8. So in that way, it can actually learn from the past and optimize my space and do that very efficiently and very quickly. So very huge improvements here as well in the hyperparameter optimization. So its model finishes at different time, at which point we kind of update the space. So the code for this, it's like that. So you have to create a function we are optimizing or minimizing in this case. And this is the optimization function. We need to define the training function, as in what is the training we are doing, what algorithm and etc. we are doing. The search space, where we're defining which parameters out of all the model parameters we're optimizing for, and where to look, as in some min-max boundaries, and then how many evaluations we're going to do, because it can run forever if you want it, right? Or you can say stop it when you run like 100 different trials and give me the best result out of these 100 different trials. And some things to remember is, so with the Spark trials, we evaluate its model on one Spark worker. So one Spark worker will have one model. And it is limited to tuning simple machine learning models. But for distributed ML models, you can use not the Spark trials, but the trial class of Horvath. So you can use it with any model, to be honest. It's very flexible. But if you use single node models on Spark, you have to use the Spark trials. If not, you need to use the trial class. But it's very flexible, so you can actually optimize any model with HyperOpt. It's the default to-go algorithm for optimization of parameters. So we went through data preparation. So we learned how to prepare all of this data. We trained our models in different ways, distributed or non-distributed. We tuned our models in a parallel way with HyperOpt. And the last thing is, since we have now a model trained, okay, how do we scale it across when we predict now? So when we have the model and we want to use it in production, so we want to predict which of our customers are going to churn or which customer is going to buy, we need to have this model live, and we need to do predictions on this group of people. So in order to do that, what we can do is we can use another UDF, which is called Pandas Scalar Iteration UDF. And what it does is you load the model, you load it in a script, right? So you load the data set as well you want to predict. So this can be, usually this makes sense when you want to predict on a big batch of data, not when you're hitting APIs. So when you're hitting APIs, you don't really need PySpark or distributed power there. But for batch inference, as we call it, when you have a huge data set and you want to predict on, this scales very well, and it can scale to any data set size. So you load the data set. From the moment you load it, because this is completely random, it splits the data set across the workers as we saw, nothing different. So we load the model, we load the data set with Spark. So from the moment we load the data set with Spark, they are across different workers. And then we predict. In Python, it's just .predict, right? So you just predict the output, and then you get the predictions, which can vary, right? So it can be yes, no, whatever, right, for your bots. And it's so simple. It's literally just a last one-line command. It's very scalable and can be very well optimized for big models, heavy models, and you can just load it and cache it and have it running very quickly. It's like so impressive that this can just do predictions very quickly, and it can scale so much. It's great. And it looks like that. So you have the predict, right? And you kind of load your model here. It's like a classification, customer segmentation in this case, customer segmentation model. You have your data frame, right? And then this, you just say model dot predict the data frame, and this just does that, and it's a pandas UDF decorator again outside of this function that does the prediction of that. And that is it. So you decorate it, you say it's a pandas UDF. I'm expecting to have a string, or it's a string if it's a class, it can be an integer, whatever. And I'm passing my data into the predict, and I'm predicting, like applying the algorithm on the data set. And it just scales across different workers. So in this way, we saw what we can do from data preparation perspective, model training and tuning, and also model inference. So we actually summed up the whole ML lifecycle of ML lifecycle. Like if you're familiar with the machine learning world, we go from data preparation always to model training, tuning, and model inference. And some things to take away is that the data is growing so much so that at some point you'll have blockers stopping you. So you'll have to move to the cloud, and you'll have to find ways to optimize your workload in the cloud. And there are different optimizations and distributed systems you can try. And today we saw Apache Spark on how you can use Apache Spark on ML problems to scale them. And remember that an ML problem can have many different steps, right? Some of these steps are owned by data engineers sometimes not. The ML team kind of ends or is responsible for end-to-end all of these. But you have to understand that everything starts from your data and how you load your data into your memory. If you can do optimization there, as in skipping and pruning on files, that is amazing. You can just be so much more optimized from the beginning. And then you can scale your ML in different ways, as in use distributed libraries or not, and use hyperparameter optimizations to tune your parameters faster, and then you apply your predictions in a distributed way. Does this make sense? Does this make sense?
Sure.
Any questions? No questions. Oh, what is Spark context? So how I'm going back. when you set up Spark, right, every time you run a Spark session, as we call it, there is a Spark context that keeps track of what's happening in this session and how much resources are being used, right? So it's something that's run on the master node, and that is the main purpose of its existence, right? To just maintain and support whatever is happening in this session of Spark at this point in time in this cluster. Yeah. And in general, now we saw like Spark in a very ML focused way, but there's a lot of data engineering and like streaming things that maybe are something you have to kind of have your eyes open for, because yeah, it can actually help a lot with big data in general. Yes, so how common is the use of single model ML algorithms in the industry? Yeah, so mainly don't think that machine learning world is kind something that it's yes so advanced. There are companies that actually use very basic machine learning algorithms in production, as in XGBoost algorithms, sklearn libraries, if you're aware. So usually they go for the simplest or the easiest implementation rather than that something very complicated. And all of these very pure Python libraries are not distributed. So usually what we usually implement with them is what I said here before, like the group key. So this one is something that we see a lot, as in very simple algorithms, but scaled based on a group key, or the hyperparameter optimization is something that is used across every customer. Now, if you're asking about Spark ML algorithms, usually they are not heavily used because no one faces yet the problem of all of these huge big data sets. Because to train a model, if it's not for kind of computer vision models or like very heavy deep learning models, where again we go into a different way of working with those, there's no need to actually use all of these huge data sets for a model, right? So usually we are going to sample down. Usually you are going to kind of select a subset of data. So you can fit it usually in one VM. So that's why the distributed libraries are not that much used, because also it's a direction from us saying that, look, if you can fit your data in your machine, just go with the things you already know when they are heavily used out there in the world. Less maintenance from your side as well. Maybe you have already code that you can reuse. Yeah, what is interesting, it's more in the deep learning world where you have to train huge algorithms on images or voice or text, where again these are not distributed either, but you have different ways on working with them, as in feeding the data in small batches instead of feeding the whole data set as these non-distributed algorithms usually work, if this answers your question. Is there any alternative to pandas that could be used on Spark? Yes. So as we said here before, there is a re-implementation of pandas on, it's called pandas on Spark. And before was known koalas. Maybe you've heard koalas. Now it's not called koalas anymore, but it's called pandas on Spark. So you can import it as this, import PySpark pandas, import PySpark.pandas, and you have more or less all the functionality of pandas re-implemented, and you can use it on Spark straight ahead. Just import it, use it, and just scales any pandas data frame manipulation you would do in pandas before. So it's a really easy transition, like for a team that works mainly on pandas, and for some reason you want to move to Spark environment. It's a very easy way, right? So you just change the library, write some tests, make sure that the results are correct, because it's a re-implementation, right? But the main functionality is there, so it should be very straightforward to use. Any other questions? Yeah, so HyperOpt is neither of the two. It's not random search, and it's not, what did you say? And it's not grid search either. In the sense, where are we here? So when we spin up these four different things, these four different experiments, and we copy the data into the machine. The first choice of hyperparameters we make is actually random, because randomly we choose four different sets of parameters to train our algorithm on this data. But it's called Bayesian because what happens, as we saw here, is so we spin up four different runs that are random, independent of each other as of now. No one knows about the other thing at all. So up to here, it could be a random problem, but it's not, because when trial one finishes, what happens here is this guy returns the results back to the driver. This is running on a worker. So when it finishes, it gives the results back to the driver. The driver keeps track of the hyperparameter space I'm having, and the distribution, as in what is the probability, not the distribution, the probability of my next best hyperparameter combination to be here versus somewhere else, based on the cost function it got from here, and optimizes, move this space and this probability space. And based on this new now probability space, it chooses a different set of parameters and kicks off trial 5. And it waits. Now trial 2 and 3 finished. These results go back to the driver. Driver updates the hyperparameter space. And based on this new, more limited now space, because every time the space gets updated, it kind of limits the space, right? Limits the space under which we are choosing parameters. Then I'm kicking off new trial 8, and etc., right? And that's why it's not a random problem, because I'm actually feeding the information back. So yeah, it's not grid search, because grid search is also random. I'm choosing different combinations and I'm trying all of them till exhaustion, right? Here, we're not doing the same. Here, we're not trying all of them. We're moving the space towards the cost, as the cost function guides us to, right? No problem at all. Any other questions? If not, sorry. So if not, feel free to connect with me and let me know how your ML problems or data problems go. You can find me on LinkedIn. And yeah, reach out if you have any questions or anything else that you want to ask me. And otherwise, I'll see you soon.